Let's take a look at this problem. Hydrogen at a pressure of 230 kPa and a temperature of 100 degrees C. What is the density of the hydrogen? Now we'll use this form of the ideal gas law, this R bar over M. This is this quantity here is often what they just call R, but my book has R bar over M in the back, so we'll kind of use it this way. So we want to find out what the density is. So you could do this a couple of different ways. You could, I'll just do it this way. I'll solve for the specific volume and then convert to density. That'll kind of just give us an extra operation we can do just so we get used to this. So I'll divide both sides by the pressure P, like this. And then if we look in the back of my book, again, this is the excellent book by uh, Kaminsky and Jensen. And I'm showing in the back of my book here that hydrogen has an R bar over M of 4.124 kilojoules per kilogram K. And now we want to multiply by the temperature, though the temperature's in degrees C, so we're going to have to add 273.15 to get us in degrees K, and then divide by the pressure. And the pressure is 230 kPa. Now, we want to be sure that all our units work out. So we should convert some of these, see exactly what we have here. So now kilojoules, again, I'm kind of going to do this a long way, but just to verify that we have all the right units. Now, kilojoules is 1,000 joules, so we can change that to 4124. And then also, remember kilojoules, or excuse me, a joule will be a Newton meter. So we convert it to joules, and then 1 joule is 1 Newton meter. And then over here we have what, 373.15 K. And in the denominators, remember 230 kPa, again, that's 230,000 pascals. And again, a pascal, remember, is a Newton meter squared. So we'll see how our units are working out here. Again, we'll cancel our K. The newtons will cancel. The kilograms won't cancel. Now we invert this. Remember, if you have a fraction over a fraction, take the reciprocal and multiply. And so we'll end up with a meter cubed up here and kilojoules here. So that's looking good. Meters cubed per kilojoules. That's a specific volume. And when you put this on your calculator, you end up with 6.69, as I said, meter cubed per kilograms. And then remember, density is equal to 1 over the specific volume. And so in this case, it's going to be 1 over 6.69. And there's a few more digits. So I'm going to just invert what I have in my calculator. It might have come out exactly the same. Put 149. kilograms per meters cubed like that. So there we have it. Now, at the beginning here, I just went ahead and solved for the specific volume. Of course, you could have put 1/rho up here and then I'm just solving for the density. But I wanted to put this in just so would have like one more conversion for just a little bit more practice. Let's take a look at this problem. A 0.3 pound mass aluminum ball at 500 degrees Fahrenheit is placed into a zero point 0.1 cubic feet of water, and the water is at 60 degrees Fahrenheit. Find the final temperature of the ball, that is of the aluminum ball, after the aluminum and the water reach equilibrium. Assume that the tank contains water that it's well insulated. In other words, the tank is well insulated. There's no heat transfer from the outside of the tank in or from the inside of the tank out. Let's take a look at this. So here's some assumptions. We can assume there's no work being done. Assume the pressure is constant. And since there's nothing flowing, there's not going to be any change in kinetic energy, so that's going to be zero. And since we're not dealing with a lot of differences in elevations, we can say that the change in potential energy is zero, and that we have constant specific heats. Now, also for solids and liquids, you recall that we can say we can assume that CV is going to be equal to CP. So if we can find one or the other of those, then we can assume it's equal to the other one. And actually, we can maybe start with that. We can maybe look up the properties. In my book, I'll look up the properties for aluminum, and you can see the density is about 168 pound-feet squared, and CP is about 0.216, although that's at 540. Now we're going to end up being, when we add 460 to our 500-degree ball, that's going to be around 960. So over here, they have a little bit more specific values. So at 1080 degrees R, looks like the CP value is about 0.246. We're a little bit less than that. I'm going to maybe estimate it at about 0.24. So write that down for the aluminum. Again, CP is going to be equal to CV, again, for a solid, and their density is 168. And then also, we're going to look up the properties of water. Now, we're going to be at about 60 degrees. So, at 60 degrees water, the density is 62.3, and our CP is 1. So we have this. And so now we can start doing some calculations. And keep in mind what we're going to be dealing with. We're going to be dealing with internal energy because, again, the other energies are zero. And so, again, the internal energy is the energy contained within the objects. And so we're going to be using change in U. Remember, this is the internal energy, and it's going to be M CV delta T. Again, I put CV here, but again, for solids and liquids, again, CP and CV are the same. So you could almost just put a C there if you wanted to. And so that's what we're going to use. And also, we're going to end up needing the mass of the water. We have the mass of the aluminum. So mass of the water is going to be the rho of the water times the volume of the water. In our case, again, we just determined that rho is 62.3 pound mass per foot cubed. And then this will be 1.1 foot cubed. So that's going to give us the mass of the water is going to be 6.23 pounds, like this. And now, again, whatever heat the ball gives up, the water is going to retain. So we can set this delta U again for the ball equal delta U for the water. And so we can put, again, that, let me write it here first. So again, we call that ball. And I'm going to just put C of the ball, as we said, the specific heat CV and CP are the same. And delta T of the ball. And whatever it gives up, we'll put a negative there. The water is going to gain. And so now we can fill in some of these numbers. We know that the mass of the ball was 0.3. CP of the ball was this. And by the way, it doesn't matter if we have an R here or an F here because it's going to be the difference in the temperatures. Like when you look in the back of the books, it might have an F here, an R, but it's always being multiplied by differences. So it's going to be the same no matter what you're using. I'm going to convert, though, the original temperature to Rankine. And so I added 460 to our 500 degrees of the aluminum. And then on the right-hand side, I don't know if I'm going to be able to fit that all in. So I'm going to put it on the next line. This is going to be 6.23 pound mass times, we said C for the water was 1 BTU. Pound mass R times T2 minus, instead of 60 degrees F, I'm going to put it in Rankine, so it's going to be 520. And again, notice we're assuming equilibrium at the end, so we're assuming this T2 and this T2 are the same. If we didn't wait for equilibrium, we couldn't have the same value here. We're assuming they're going to reach equilibrium. So I multiplied this all out. I distributed this over here, multiplied and distributed among these two. Same thing on the right-hand side, multiplied and distributed these. And now what I'm going to do is put all the t's on one side and the constants on the other side. I'm going to put them such, let me see, what would be the best? I'll maybe, we could do it either way. You could either move everything to the t's to the right and the constants to the left, or the t's to the left and the constants to the right. I'll move the t's to the left just to make it look a little bit nicer. And when we do that, on the left, we're going to get minus 6.302 BTUR T2. And we put the constants together. We'll end up with minus 3308.7 BTU like this. And we divide both sides by 6.302. We end up getting that T2 is 525.02 degrees R. Or if we subtract 460 from that, we will end up with T2 is being what, 65.02 degrees F, like that. Now, just a couple things to notice, and looking back, I probably made the wrong choice for my C value for the aluminum. I picked it based on the 500 degrees, but you can see when all was said and done, it ended up going down to 65 degrees. And so really, I probably should have picked some average in between. So if you wanted to, you could go back and do the whole thing again with maybe the average of the 65 and the 500 and use that CP value. But it's not going to change it a whole lot. And notice now the water temperature didn't change much. It started at 60 and it ended up at 65. So that CP value was probably correct to use that. Again, now looking back at this, another assumption I made that I didn't write down is I assumed the whole system was isolated from everything. You know, and it's probably that was a assumption that probably isn't 100% accurate because this ball was dropped into this water. That means the top would have been open. But so I'm kind of assuming here the ball was dropped into the water and then somehow the system was isolated and there was no air or anything in here. And the reason you want to do that, of course, you just want to have the two medium, the aluminum and the water. Otherwise, it gets a little bit more complicated, but it's not an unreasonable assumption. Next, let's take a look at this problem. Now, this problem is from our textbook, and consider figure 1. And this is a cylinder with a spring and piston. And nitrogen at 28 degrees Celsius and 100 kPa is heated in a piston cylinder assembly. The spring stiffness is 28 newtons per centimeter. And before the nitrogen is heated, the spring is not compressed. The cylinder diameter is 5 centimeters. You can see from the diagram there what it's referring to. And the height L1 is 8 centimeters and L2 is 6 centimeters. 4 kilojoules of work are done by the nitrogen. Let me just zoom in just a little bit so you can see the actual values here. You can see L1 is that lower portion, 8 centimeters. L2 is 6 centimeters. How far does the piston rise? And what is the final temperature? Assume atmospheric pressure is 100 kPa and the piston is massless. Couple more things that we can assume here is that the spring stiffness is 28 newtons per centimeter, and the atmospheric pressure is 100 kPa. The diameter of the cylinder, and therefore the diameter piston, I forgot to put that in, that's going to be 5 centimeters. Now we're going to end up needing the area because we're going to be talking about like pressure on the piston, etc. So I'm going to find the area of that piston. And of course, the area of the piston is going to be like 1/4 pi diameter squared, or you could have used pi radius squared. Either one would work. And of course, you'd have to divide this by 2 if you use this radius. And when you put this into the calculator, it's like 0.00196 meters squared. Also, I should have noted I changed this to meters. 5 centimeters. Remember, you divide that by 100 to get 0.05 meters. It's probably more convenient to use meters uh, in this problem. And next, we're going to look at the work done. So the work done by the nitrogen on the boundary, let's say, on, let's say, the piston. I'll just call this W1. Again, that's going to be, remember, the work is always force times distance. And now in our case, the force is going to be the pressure times the area. That'll be the force. And then the distance would be maybe the height that this moves. So we could maybe consider that this is going to move some height h as the gas is expanding. So I'll just call that h there. And again, we have our pressure 100 kPa. So let's convert that. Remember what that is? That's going to be 100,000 PA, 100,000 pascals. And a pascal is a Newton meter squared. And then times the area. And then times the height. So our W1 is going to be, and it's going to be 196.35 newtons times the height. And now let's find the work done by the nitrogen on the spring. And let me just call this W2. Now, often keep in mind that when you're doing work on springs, it's going to be K times X dx, the integral. Now, in this case, again, when you integrate this, again, we're going to go from 0 to some height h. So let me actually, k is a constant, so we can pull that out. If we integrate x, that's going to be x squared over 2 from 0 to h. And then we can actually factor out our k, and we'll end up with h squared over 2 and then minus 0. If we had started with the spring compressed, then this would not have been 0 here. So we would have had k times h squared over 2 minus something else, maybe, some L squared over 2, all times k. But in this case, we started with no compression of the spring. And now let's substitute our 28. Now this is 28 newtons per centimeter. So I'm going to have to actually convert that to 28. I remember we have to multiply it by 100 to get newtons per meter. And then over here, this is going to be h squared divided by 2. So we could actually write this as 1400. And so again, we'll end up with 1400 h squared Newton meters, like this. So the total work done by the nitrogen is going to be W1 plus W2. And we're told in the problem that that's going to be equal to the work done, 4.5 joules of work are done by the nitrogen. So a total of 4.5 joules of work done, that's going to be equal, or W1 plus W2. And our W1, again, we just found here 196.35. H, or H, and actually N stands for newtons. And our W2, which we just found, is 1400. And now I'm going to suppress the units for the moment until we actually solve something. It's a little bit confusing with the H's and the N's together. And again, remember, joules is Newton meters. So we could actually replace that with Newton meters. And so we have an H and an H squared. So we're going to have to treat this like a quadratic equation. Let's move everything to the right-hand side and set it equal to 0. And that's going to be, and let me put the H squared first here. 1400. Like I said, I'm just going to suppress the units. And that's all equal to 0. So we can use a quadratic formula. And remember, the quadratic formula is negative b plus or minus the square root of b squared minus 4 times a times c divided by 2a. So when you work at this square root here, this comes out to be 252.5. Now, in our case, the negative, if we get a negative value here, it's not going to have any meaning. And so So again, if this is negative, it's going to make the whole sum negative, so we'll just ignore that. But if this is positive and that's negative, we end up with uh, something like 0.020 meters, like that. That's going to be the height that piston is going to move when 4.5 joules of work is done by the nitrogen. Next thing we're going to have to do is find the temperature of the gas. And so we're going to have to use the ideal gas law. Remember that uh, for what do we have in this case? We have nitrogen, which that's an ideal gas. So we can use the ideal gas law. Now, when we go to calculate the ideal gas law, we're going to need the pressure and the final pressure as well as the mass of the gas. And so we're going to have to start with our given condition to find the mass of the gas. Again, remember for the ideal gas law, we'll have like P1, V1 is equal to this in our initial case. Now, again, remember this is specific volume, but we're going to need the mass. So we can replace that specific volume with the actual volume divided by the mass. And then we can solve for this. So you can see if we can solve for mass by dividing, by multiplying the m over here and bring this over here. Now I'll kind of change sides to while I'm doing that. So this is going to end up being P, and actually this should be a V1 here, by the way. P1, V1. Now I move the M to the other side. And then here we're going to have R, M, and then T1 here like this. Now for the initial pressure, we had 100 kPa. Again, remember that's going to be 100,000 pascals. And again, a pascal is a Newton over meter squared. And then the initial volume, we're going to have to calculate. We know the area of the piston, but also we know the height. So if we take the area times the height, that's going to give us the volume. So let me take the area, which was 0.00196 meters squared, times the height. Again, this is the initial volume, and 8 centimeters, that's going to be 0.08 meters. And then for R, again, if we look in the back of the book for nitrogen, our R bar over M is going to be 0.2968. That's going to be kilojoules per kilogram, degrees K. And then the T1, our initial temperature was 28, but it's going to have to be in degrees K. So we're going to 28 plus 273.15. And that's going to be K like this. Now it's a bit confusing because I have meters here on this side, and on this side, this is mass. So maybe let me just put a star by the mass here to realize that that's mass, and these are meters over here. But let's just check to be sure things are working out correctly. And let me just make one change here. Here we have kilojoules, and let me turn that into joules. So I'm going to multiply by 1,000. So that's going to give us joules when I multiply by 1,000. And also, joules, remember, is a Newton meter. That's a little bit messy there, but hopefully you can read that. And so if we look here, the K's cancel. And up here, we're going to have these M squareds will cancel. Then you have an M here and an M here. Those are going to cancel. The newtons are going to cancel. And then because this is a reciprocal down, this is a fraction down here, when we take the reciprocal, multiply through, we're going to, in fact, end up with kilograms. So that's a healthy sign. And when I calculate this big mess out here, I end up with a mass of 1.754 times 10 to the minus fourth. And like I said, we determined that this all reduced to kilograms, which of course what we would expect for mass. And so that's going to give us, so we use the initial condition to find the mass. Now again, we want to use ideal gas law. Now we need the final pressure on the gas. And so the final pressure is going to consist of the pressure from the spring. And so let's actually write that down. The pressure from the spring is going to be like our K times our H. Actually, maybe let me write it sort of this way first. See if this makes a little bit better sense. This is going to end up being force divided by area. Now, the force from the spring is going to be K times the height that it was compressed, right? And divided by the area of the piston, because that's going to be the area that's distributed. And so let me write that like this. And again, we said that K was 2,800 Newton meters, Newton per meter. And the height that we ended up compressing the spring, we just found was 0.02 meters. And we'll divide that by the area of the piston, which we found before, 0.00196 meters squared, like this. And let's see, meters cancel. Here's where we have Newton over meters squared, which that's what we would expect for pressure. And so the pressure of the spring end up, caused by the spring is going to be 28,571 Newton per meter squared. So then the total final pressure, P2, is going to be the atmospheric pressure plus the pressure from the spring that's caused by the spring. So again, remember the atmospheric pressure is going to be pushing down here. And we're told again it's 100 kPa, which is 100,000 pascals, which is the same as 100,000 Newton meters squared. So our final pressure on the gas is going to be 128,571 Newton meters squared. I probably should have reduced the significant digits. We don't really have that many available, but you can fix that. So now we can finally use our ideal gas law. Again, I just realized we're going to need our final volume. Now, the volume is actually going to be the area of the piston uh, plus this total height here. Now, since I've called this H, I'm going to just call this total L. And L is just going to be the 8 centimeters plus the amount H was that's a 0.02 meters. So it'll be 0.02 meters plus 0.08 meters like this. That's going to give us our final volume. And this is going to be our V2 is going to be 1.96 times 10 to the minus 4 meters cubed like this. So that's going to be our final volume. And so again, we're going to go back to our ideal gas law. And now we're going to have it's state 2. Again, once again, I'm using mass star here to distinguish it from meters. And so this is going to be P2, V2, mass star, and divided by this. And again, we'll substitute in our values for P2. We found that a minute ago, 125.71. And our volume, we found that up here, 1.96 times 10 to the fourth. Now I moved the mass down into the denominator here. Again, we found that a little while ago, 1.754 times 10 to the minus fourth. And excuse me, we originally had 0.296 kilojoules per kilogram K, and then we converted that to 296.8 joules, which is saying 96.8 Newton meters divided by kgk. Again, we did that back in this step here to get that. And again, like I said, the mass was this. And when you put all this into your calculator, you end up getting T2 to be 484.07. And now again, let's check the units here. The newtons are going to cancel. This is going to cancel, leave us a meter here, but then that'll cancel. And the kilograms are canceled. Then we have 1 over K in the denominator. Then we do the reciprocal. We get this. Then when we subtract 273.15, we end up with 210.9 degrees C like this. Next, let's consider this problem. This problem is from the textbook. Air at 30 degrees C is contained in a piston cylinder assembly. See figure 2. The piston has a weight of 15 newtons and a cross-sectional area of 0.12 meters squared. The initial volume of the air is 3.5 meters cubed. Heat is added until the air volume becomes 6.5 meters cubed. Use atmospheric pressure of 100 kPa. Determine the final temperature. determine the work done by the air on both the piston and the atmosphere. 3.5 meters cubed, then the final volume is 6.5 meters cubed. Now, this piston is just sitting on top of the air, so we can actually calculate the pressure that it's putting on. Now, there's the atmospheric pressure plus the pressure of this. So the pressure from the piston itself is going to be just the force over the area. And so actually, again, we'll call this P. Now, the pressure is going to stay the same because, again, this piston and the atmospheric pressure are both keeping the air at a steady pressure. And so it's going to be the 100,000 pascals, which again, remember that's Newton meters squared. And then plus over here, we have 15 newtons divided by our piston area, like this. And so the total pressure is going to be 125 Newton meters squared. And now the initial temperature is 30 degrees C. That's we 30 plus 273.15. .15 degrees K. And let's see. So we probably want to, now you could actually manipulate the equations and work it out that way. A lot of times what I like to do is just actually find the actual mass to start with. So again, we're going to have P1, V1. I'm going to write it this way. I'm going to write mass with a star again, equals R over MT, like this. This here. Again, if we solve for mass, that's going to be P1, V1 by R M T. Excuse me, up here, this should have been, I don't know where I got the T2 here. This is just T1 up here. And again, from the back of the book, the R over M is 0.287. That's in the denominator. The pressure, we just found that up here. The initial volume was our 3.5. Our initial temperature was 303.15 K, like this. And let's just check to be sure our units coming out right. Again, the K's will cancel here. The Now the kilojoules, again, we can convert that to joules, which is 287. But then a joule is a Newton meter. This kind of messy. But again, the newtons will cancel. And the meters cubed here, meters squared. This would be meters cubed. All the meters cancel. The K's cancel. So we have 1 over kilogram in the denominator. We do the reciprocal. That means kilogram. That's what we expect for mass. And when I put this in the calculator, I get 4.03 kilograms. Now we can go ahead and apply the ideal gas law to the state 2. And so we can use this up here. We want to solve for T2. So I'm going to use the same equation except with P1, excuse me, P2, V2, T2. And so I'm going to solve for T2 up here. So T2 is P2, V2 over R over M times mass. And again, our pressure is going to be constant because we have this piston keeping it at a constant pressure in the atmospheric pressure. So we're still going to have this 100, 125 Newton meters squared. And then the volume is going to be 6.5 meters cubed. And then once again, for R bar over M, we have 287 Newton meter kilogram K. And then for our mass, we found that up here, 4.03 kilograms. And we put that in the calculator, comes up to 562.99. So I think we can round that off to 563. And let's just check the units. Newtons will cancel, meters cubed divided by square, but then that'll make it cubed. The meters cancel, the kilograms cancel. So we only have 1 in the numerator, then 1 over kilogram denominator, excuse me, 1 over K in the denominator. So that's our temperature K. And again, if you want to convert it to Celsius, T2 is going to be approximately 289.8 degrees C. So the last thing we have to do is find the work done. Let's do that. So this is part B. The work is going to be integral of P dV. Now, one good thing is, remember, our pressure is going to be constant, so we can factor that out. And so we integrate, that's going to be like, and to say we're going from V1 to V2, that's going to end up being PV2 minus PV1. Again, the pressure is constant. And so that's going to be the same. You can write this also as P delta, the volume, like this. again, and the constant pressure was at 100, 125 Newton meters squared. And the difference in volume is going to be our 6.5 minus our 3.5 meters cubed. And of course, that's going to work out to be Newton meters, which we would expect for work. So the work is going to be either 300, 375 Newton meters, like this. And of course, Newton meters is the same as joules. And if we divide by 1,000, that'll give us kilojoules. You can rate the work this way, or rate 300.4 kilojoules. Let's take a look at this problem. The piston cylinder assembly in figure 3 contains hydrogen at 30 kPa and 10 degrees Celsius. A 3 kilogram piston with a diameter of 0.1 meters rests on a set of stops, and the height h is 0.08 meters. How much heat must be added so that the hydrogen just lifts the piston off the stops? Now, if you have a hard copy of this, yours may or may not be figure 3. It might be a different number because I've been rearranging these. But in any case, let's take a look at this problem here. So the problem looks something like this. We have hydrogen, 30 kPa, 10 degrees C, and the atmospheric pressure is 100 kPa. The piston is 3 kilograms, and the height is 0.08 meters. And we should put down some assumptions. And again, so there's nothing flowing, and so we can assume the change in kinetic energy is 0. And also, there's no major change in height of anything. Yeah, maybe this gas will expand a little bit, but again, we just wonder when it's gonna lift the piston off. So there's going to be really no change in elevation. So we can say the potential energy is going to be the change potential energy is going to be 0, and that also we can assume these stops here are of negligible size. So stops are negligible size. In other words, they're not too wide or too thick to affect like either the volume down here or to affect the pressure on the piston. And we're going to eventually need a couple of things. We're going to be applying the ideal gas law. And so we're going to need like the volume of the cylinder. And then also we're going to need the area of the piston. So we can calculate, might as well calculate those right at the start here. So the area of the piston is going to be 0.25 pi diameter squared, or you could put pi r squared if you like. And this comes out to be 0.00785. meters squared. And then the volume, again, we're assuming these stops are negligible size. So we can assume the volume in here is going to be the area times the height, which is going to be what we just found, 00785. And the height is 0.08 meters, like this. When you put this in the calculator, you get 6.2832 times 10 to the minus fourth meters cubed. And by the way, we're going to have to find the pressure that's required to lift this piston off the stops. So we're going to have to find out what it's going to take to lift this off. So the pressure from the piston, the pressure that the piston is going to cause, and that again, that's going to be the force divided by the area. And in this case, the force is going to be 3 kilograms times 9.81 meters per second squared. And then the area we found up here, and of course, kilogram meters per second squared, that's newtons. And that comes out to 3749 meters, Newton meters squared. So that means the total pressure required to lift the piston off is going to be this pressure plus a atmospheric pressure. Now, 10 kPa, excuse me, 100 kPa is 100,000 pascals. Again, a pascal is a Newton meter squared. And so this is going to be 103,749 Newton meters squared. And actually, you can see in this case, the pressure caused by the piston itself is almost negligible compared to atmospheric pressure. So we have a lot of the stuff that we need. Again, this is going to end up being our P2 because that's what we're going to have to achieve. We're going to have to achieve this pressure to lift this piston off. But for right now, let's go ahead and calculate the mass that's of H2 there is here, because usually we're going to need that when we apply the ideal gas law. When we go from like one step to the next, from state 1 to state 2. And so let's remember, so P1 V1 over M is going to be equal to R over M T1 like this. And I put the mass as a star so that we can distinguish it from meters. So we want to solve for the mass. And so it's a matter of bringing this to this side and bringing these down here. And I'm going to write it the other way. And you can check to be sure that this all looks correct. Something like this. And now we know the initial pressure. That was our 30 kPa, which I'm going to write that as 30,000 Newton meters squared. And then the volume we had was this number right here. And for R over M, I'm using the book by Kaminsky and Jensen. And they have under hydrogen 4.124 kilojoules kilogram degree K. Now, I'm going to change the kilojoules to joules. So that's going to make us multiply this by 1,000. So it's to be 4124. And again, a joule is a Newton meter. And that's kilogram degree K. And times the temperature. Now we have 10 degrees C. We're going to have to change that to Kelvin. So that's 10 plus 273.15 Kelvin, like this. And before we calculate this, just check our units. The newtons will cancel. Meter cubed here. Now we have a square here, but we divide that by a meter here, so that'll be meters cubed. So meters cubed will cancel. So the newtons and meters cubed cancel. The Kelvin cancels. So we're going to have 1 divided by the fraction 1 over kilograms. We take the reciprocal, we get kilograms. So we have all the right units. Always good to check that. And when I put in the calculator, I get 1.614 times 10 to the minus 5 kilograms, like this. Now, in order to find the heat transfer, we're going to have to figure out what the final temperature is. And again, that's going to be the temperature at which the pressure is such that the piston lifts off the stops. Now, we could actually notice here that between state 1 and state 2, this is constant, the mass is constant, the volume is constant. So we could, in effect, just use the relationship between P1 and T1 and P1 and T2. In other words, if we have an ideal gas such that the volume, the mass are all the same, then we could actually say that P1 over T1 is equal to P2 over T2. You could sort of prove this by bringing T1 over here, bringing everything else to the right-hand side, and that right-hand side is going to be the same for P1 over T1 as well as P2 over T2. So again, you could do it that way, or if you didn't remember that, you could just do it the long way. So let's actually do it the long way just in case you didn't see the relationship. You could just say, I'm going to solve for the temperature at state T2. In other words, just solve this for T2, P1, P2, excuse me, V2 divided by R over M mass star. Like, remember, that's the mass. And remember the pressure required to lift that piston is 103,749 Newton meters squared. And the volume is going to be the same for state 1 and state 2 because we're just finding a point just at which it's lifting off the stops. And then R over the molecular weight is going to be the same as before. That was our 4124. And then finally, our mass we just found up here. And just double check the units. Kilograms canceled. Newtons cancel. Meter cube here. We put these together, meter cube here. We'll have 1 over the fraction 1 over K, which is what we went for temperature, because when we do the reciprocal, it'll just be K. And T2, then, when you put this into your calculator, this is 979.4 Kelvin. Or if we subtract 273.15, this is going to be 706.2 Kelvin. So now that we have this, we can find the heat transfer. And remember that the first law says that Q minus W delta U plus delta kinetic energy delta potential energy. And remember, we've determined these are both 0. And then for an ideal gas, this right-hand side is going to be mCV delta T, like this. And also, nothing actually moved. There was no work done to the gas. So there was no work done in this operation here. So we have this. Again, the M is the mass. And now we need CV. Now, the back of the book probably just has CP, but we can find CV from that pretty easily. Now, when we look up the CV, we're probably going to use the average temperature. So for the, we want to find the average temperature. We'll use that to find our CV. And so the original temperature was 10 degrees C, which is 283.15 degrees K, plus our final temperature was 979.4. And take the average of those two. And that's going to be 631.3 K. And we'll look up again in Kaminsky and Jensen. I'll look up under hydrogen. We want to see around 630. So for hydrogen, CP Let's see. So that's going to be about a third of the way. About a third of the way between these two numbers. And the difference there is 0.06. So a third of the way would be what, about 0.02. So we can probably say that this is going to be, CP will be 14.57. Like this. Now, again, we don't have CV, but you remember the relationship is that CP is equal to CV plus R over M. So we can rewrite this to say CV is CP minus R over M. And so it's going to be 14.57 kilojoules kilogram K. And our R, when we originally looked that up, it was, remember that was 4.124 kilojoules per kilogram K. I converted it, but it's 4.124. And would you put that in your calculator? 1044.6 kilojoule kilogram K, like this. So now we have everything we need to go back to this equation up here. And let me actually rewrite that down here. So Q is equal, again, I'm putting M star for the mass. And again, we found that the mass was 1.614 times 10 to the minus 5 kilograms. And then the change in temperature was, the final temperature was 979.4 minus 283.15 was the original temperature. And when I put this in my calculator, I got 0.1174. Let's check the units. The K's cancel, the kilograms cancel, and it looks like we're left with kilojoules, like that. And so that's the heat transfer. Now, as I mentioned on the previous page, we could have calculated our final temperature a little bit shorter way. We could have used this relationship here, and you can check that that in fact works. Again, you can try that on your own, but you'll find you will get the same answer here when you solve for T2 and substitute everything. Again, it saves you a little bit. It would save you from having to do a little bit extra calculation, but it's not that much shorter. You would still have to do this last part again. Once we found the temperature, we went through and applied the first law and ended up with that.